वेबसाइट भी अगर आप कुछ अपलोड करना चाहते हो तो वेबसाइट भी इसको ट्राई करते हैं ट्राई सर्च किया है ट्राई देयर इज अ प्रॉब्लम व्हिच para तो प्रश्न आईआईटी मद्रास सिमिलरली हम लोग आईआईटी में टेस्ट देंगे सिमिलरली आईआईटी दिल्ली के साथ टेस्ट बेंच हम लोग कोलैबोरेट करेंगे सॉफ्टवेयर पीस आईआईटी मद्रास में अगर पांच इंस्टीट्यूशंस में कोलैबोरेशन करेंगे तो सिमिलरली आईआईटी दिल्ली के साथ भी ट्राई एंड ड्यूटी का गाइडेंस सर्वाइव
Session 2 of technical presentations. And ladies and gentlemen, I have the proud privilege in inviting on stage our distinguished session chair for this session, Mr. Ayush Bhatnagar, Senior Vice President, Reliance Jio. A very warm welcome to you, sir. And also join me in welcoming our eminent speakers for this session, Mr. Michael Thedald, who is the Chief Technologist, Telco, Red Hat, APAC. A very warm welcome to you, sir. Inviting Mr. Charles Santhosan, Associate Vice President, RAN Systems Engineering, Mavenir. A very warm welcome. Ladies and gentlemen, please put your hands together to welcome him. Inviting our eminent speaker, Mr. Gil Helliman, Vice President, Telco Solutions, Engineering and Architecture, Wind River. Inviting Mr. Arif Khan, CEO and founder, CoreEdge.io. A very warm welcome. And also inviting Mr. Chitwan Arora, System Design Engineer, Hughes Systic Corporation. May I once again request our eminent speakers, Mr. Gil Helliman and Mr. Chitwan Arora, to kindly grace the stage. So, ladies and gentlemen, once again a very warm welcome to session 2 of the second Open RAN India 2022 Hybrid Conference. The topic for this session is Open RAN Infrastructure and the Future Business Model. And the time duration for this session, ladies and gentlemen, is approximately 1 hour 30 minutes, which includes the opening and closing remarks by the distinguished session chair and presentations or addresses by all our eminent speakers for about 15 minutes each. And we shall have question and answers in the end after all the presentations are over, if the time permits. With those words, I hand over to our session chair, Mr. Ayush Bhatnagar, Senior Vice President, Reliance Jio, for your opening remarks, sir, and to kindly carry forward the proceedings of this session. Over to you. Yes, sir, you can use this. And about 15 minutes for each presentation.
Yeah.
And question and answer in the end of the time permits.
I have some slides also which I've given to you.
Yeah, you can start with your presentation.
Welcome everybody. It's a pleasure to be chairing and hosting this session and this wonderful industry event. And it is also a pleasure to see an in-person attendance of so many people from the industry and also our esteemed panel. And today we will be touching upon a lot of topics, more from the technology standpoint on Open RAN, where we are and where we should be as we move forward. And even though I will be handing it over to our panelists and our presenters in a minute, but I will try to set the context of this particular session. And for that purpose, I have a few charts that I would like to present and discuss. So I think if we can move forward to the very first chart. Okay. Yes. So first of all, I believe there is a promise of Open RAN that has been mooted in the industry, that how Open RAN is going to transform how telecom networks are designed and how telecom networks are going to scale as we move into the 5G era and beyond that. So this is just a slide which kind of summarizes some of the promises that Open RAN has set out to achieve. Of course, in the disaggregation of both software and hardware, the commoditization of the RU, DU, and CU functions, which is also very well specified in these standards bodies, and also an opportunity for carriers to innovate and to make the best of the Open RAN ecosystem in terms of the suppliers and in terms of the technology providers. So this is the big picture and the promise of Open RAN. How much we have achieved this promise and what needs to be done, we will be discussing as part of this particular session. Now moving forward, I believe there is also a very good confluence between Open RAN and Edge, and I believe we have RF here to talk more about edge computing. But as we all know that some of the Open RAN functions can be deployed on edge locations. Those edge locations may be the far edge, or those edge locations may be somewhat nearer to the data center. So how that pans out and how that is going to catalyze the adoption of Open RAN and its scaling in the mid to long run, that is another very interesting thing to discuss and to deliberate on. Then, of course, is the standards part, because no initiative is complete without standardization. So as we can see in this particular diagram, we have the standardized interfaces between the various components of the Open RAN stack, and also the Open RAN components and the northbound, such as the RAN intelligence controller and the cloud native OSS and BSS. So it is interesting to review where we have reached vis-a-vis the maturity of the standards and the adoption of these standards in commercial offerings, and what needs to be done to make it ready for prime time and GA. Even though a lot of work has been done, but a lot more needs to be achieved. Then, of course, the opportunities, like we spoke about, there are opportunities for carrier networks, there are opportunities in enterprise markets, there are specific use cases both in rural, suburban, stadiums, campuses, where Open RAN has a role to play. And also there are certain aspects of advanced network management and automation that come up because of the openness of the radio components themselves, which were otherwise not so straightforward with traditional RAN solutions. So this is another implication of Open RAN. And of course, to what extent Open RAN benefits both the CapEx and the OpEx outgo for carriers. Then just to put it all together, Open RAN, it applies to all the flavors of radio products, whether it is a macro G node B, whether it is an indoor solution, whether it is an outdoor small cell solution, whether it is a 44R based configuration or a 32T or 62TRX based massive MIMO active antenna configuration. So all of them are candidates for Open RAN adoption and implementation. And to complete the whole story, we have a whole suite of automation platforms that carriers can probably leverage and to further bring down their OpEx as they operate a large Open RAN based network at scale. So this is to just set the context, and moving forward, I would like to perhaps hand it over to our first speaker of the day, Michael. I believe it's your turn. And he's the chief technologist at Red Hat in the APAC region, and we will let him introduce himself and to give his perspectives in this session. Thank you.
Thank you. Good morning. It's good to do an in-person event. It has been a very long time for myself, maybe for many of you. So it's nice to see so many people. And so thank you for having me here, because it's really a great experience. And I think it's quite exciting. Since I've been in Asia Pacific, for me, I've been in the area of virtualization of the network since the very beginning, since 2010. And I must say, India is the most innovative country in this area. For some example, you have the most innovative telcos, I would say. Your peers in APAC, except they're quite, I would say, conservative. And so it's always very exciting to deal with India, because here people are not afraid to adopt new things. Although maybe 5G is late, but when it comes to the virtualization of the network, the open horizontal telco cloud platform, it's really happening in India. So I'm very excited to be here. So today I'm going to talk about the platform, the importance of the platform for Open RAN, and more importantly, the importance of the platform in general, and also the importance of the collaboration between the industry players and the ecosystem. Okay, so let's move to the first slide, and I control this here. Okay. Oh, the wrong button. Okay. So first of all, I'm going to put back the platform into the context. So here you see the kind of different variations you can have for a mobile network. But wait a minute, I forgot one slide. Yeah. So yeah, in this whole, let's say, Open RAN concept, there are two types of opennesses that we have. On the left-hand side is the openness and the choice and the freedom to mix, let's say, CU, DUs, RUs from different vendors. Okay, that's usually very important to when we go to see, the RAN department in a telco service provider. That is very much their focus, because it's really about opening up, some of the interfaces in the radio access network, which have been traditionally not completely opened, especially the interface between the RU and the DU. Okay, so this is usually top of mind when we go to see a RAN department. What's something, and it's not surprising, is not top of mind, is the second openness. The openness between the workload, the radio access network workload, and the underlying platform. In fact, I was talking to a colleague last week, and he told me, the first time we went to see the head of the radio, let's say, department in Telefonica, he asked, okay, why I'm going to see you, Red Hat? Why do I have to do any business with you guys? Okay, so usually in the radio department guys, they are not focused on that type of openness. Okay, but I'm going to focus on the right hand of this slide, which is very much about what it takes to have an open platform which can host workloads, radio access network workloads from different vendors. So this is what we call the open telco cloud platform. So in a little bit more detailed, there are some variations around it. So you could build, let's say, a radio access network which has these open radio interfaces where you can mix and match RUs with the same DU, but it can still be based, on a complete vertical stack from a radio point of view. This is the first line of this slide. Then here we are talking about Open RAN, so it's really about having everything open. But even, let's say, the traditional vendors like Ericsson and Nokia, they are also offering, in fact, their workloads, which from a radio interface point of view are not completely open, but they can offer them also on a telco cloud platform, which is not theirs. Okay, so this is, in our language, internally, we call this kind of vRAN. Okay, in marketing language, sometimes they call this Cloud RAN. That's the second line of this slide. And then, of course, I think what you are looking here is the complete openness, having both the openness in the radio interface and the openness towards the underlying infrastructure. So we kind of like to call this open vRAN. But clearly, I think what India is looking for is to have this, because this is where you have the maximum choice and the freedom to have, let's say, new players that can open the ecosystem. So we are going to focus on that. As you can see, the focus is going to be the red layer, which is the platform, the virtualization container platform that is hosting these workloads. So the telco cloud platform is not something new, because it started all for telco service provider, it started in the mobile core network with the initiative called the NFV, which the term was coined in 2012. So that's how the virtualization and the disaggregation started first. And in fact, so with Open RAN, we have the opportunity to extend that Open Telco Cloud from the core of the network to the near edge and the far edge. And the first workload is the radio access network working workload. But this brings, let's say, new requirements to this telco cloud platform that were not, let's say, necessary for the mobile core. So we have just highlighted some of these. So for example, the DU, in fact, and it's mostly about the DU. The DU is a very demanding workload because it processes a lot of data coming from the, from the antenna, from the radio antenna. And of course, this has to be done very quickly, which means that the kernel and the operating system that has to do this, it's usually required that it supports real-time features. Real-time features is not so much about, processing a lot of data, but processing data in a deterministic way. Because if you lose, a frame coming from the radio, and then at some point in time this happens too often, you're going to lose the communication. So in fact, the real-time kernel is some of the very important requirement for the DU at the far edge. And it's not something very common, let's say, and very easy to master in the industry. In fact, we have learned this the hard way. The first time we had to do this was in fact in the Rakuten mobile network a couple of years ago. And in fact, we had to optimize the real-time, let's say, Linux kernel to address this type of workloads. And when I was talking to one of the consultants, who was on this project, when we started doing this and testing in this lab, he had never seen a Linux kernel crash so many times. So these workloads at the beginning, they were crashing the Linux kernel. Okay? And then we had to, of course, enhance, fix the bugs, and then ultimately, have a very, let's say, battle-proof real-time Linux kernel. So that's one of the key, let's say, ingredients. The other one is, okay, and I think everybody in the radio industry know that, it's time and synchronization. But when in the ORAN, let's say, in the Open RAN world, time and synchronization is provided, in fact, is the responsibility of the telco cloud platform. So it becomes very important. And then there are features like, PTP and soon also Syncy, who are very important. And they need to be tuned and optimized in the underlying Linux kernel as well. And the third one, again, this is linked to the amount of data. Usually, the CPU that you have, let's say the common Intel CPU is not powerful enough to process that amount of data. So you need hardware accelerators. First generation, let's say Open RAN networks, they used FPGAs, but now maybe you have also some more ASIC-based hardware acceleration card, but you need some form of hardware accelerator that need to be supported by the underlying platform. And then there's some work that we have done, doing, let's say, time synchronization in the Linux kernels. We have been working on this for quite some time now. And then you have, let's say, other things, which some of them have already been, let's say, needed for a mobile core, which is, for example, the importance of sometimes pinning workloads to CPUs, or to specifically, let's say, one of the two CPUs in a server. We know these ones. And I think this has been highlighted, and I will not dwell too much about it. The automation is is paramount, and in industry you call this zero-touch provisioning, because at the edge, we are talking about hundreds, thousands, 10,000s of sites that need to be deployed and then maintained. So this is impossible, without a very aggressive automation. So zero-touch provisioning, having a complete automation for deploying a radio site, from turning on the server, installing the base operating system, adding the Kubernetes platform on top, and finally, turning on the workloads, then going with the server to download the configuration, the radio configuration of the workload. All of this needs to be automated from an end-to-end point of view. So that's, I would say, on this slide, that's one of the key thing that needs to be done. The second one is also low latency. Again, this is related to, that is very specific to the DU. You need to have deterministic processing of the data, but also it needs to go quickly through your Linux kernel, so that again, you don't use the radio signal and you can keep up the call. But now let's step a little, I would like to step a little bit back and just let's think, what are you going to have at the edge? And in fact, this is a picture of the near edge that you see here. Okay, so yes, here we are here to talk about Open RAN, which is about having a different radio access network, virtualized, containerized. So that's the the block on the left-hand side. But at the same time, we are doing this to have a return of investment, and we want to monetize this network, which means that telcos are also exploring, edge computing use cases, MEC use cases. So that's the right-hand block. That's quite important for the monetization of the network. That's how all telco service providers hope to have a return investment on 5G. But enable to put this application closer to the user, typically at the near edge, you also need to terminate the mobile network, which means, in fact, you need to distribute your mobile core more than before, and that's the block in the middle. So it means you also have, at the typical near edge location, you will have a distributed, UPF, and to terminate the mobile network, and then hand over the packet and the data to the MEC edge computing application that sits there. So this is the three types of workloads that you would typically have in the future in a near edge location. And what are the requirements, for these workloads? Sorry, it makes sense, in fact, to have this hosted on a single platform. For a very simple reason, is because at the edge you have space constraints, you have electricity constraints, you have cooling constraints. So you don't have the luxury, of a big data center, and it's not necessarily possible to deploy 3 different platforms, for each of these workloads. Maybe in some large locations, maybe in some, in some big cities, you have that luxury. But, in some cases, you will not have that luxury, and it makes us, just because of the resource constraints, it makes sense to have a single platform to host these 3 types of workloads. The second reason is, of course, from the point of view of the telco service provider. It provides you, consistent operations. Your teams have to learn just one platform. It's easier to operate, and it's also, I would say, it's easier to add and remove things faster. And the last thing is, it's just, it enables you to have more innovation because because of the simplicity. This is the power, of a cloud. The value of a cloud gets greater the more workloads you have on it. If you need a specialized cloud for every workload, it's not a cloud. It doesn't make sense at all. Okay? So we believe that it's in the interest of the telco service provider to standardize, especially at the edge, on a single, let's say, open telco cloud platform to host these workloads. Okay, here are the requirements of the workloads. I already detailed the one for the radio access network. So let's focus more on the right-hand side, which is the interesting side, which is the monetization side, and which is edge computing and MEC. And here the requirements are quite different. Here on the left-hand side, we are talking about real-time, time synchronization, low latency, these kind of things. On the right-hand side, there are quite different properties that are important for edge computing. First of all, I think nobody knows what's going to be the successful, edge computing application right now. That's the big question in the industry. Where should I invest? Should I invest in edge for retail? Should I invest in edge for healthcare? Should I invest in edge for energy? Nobody knows, frankly. Okay? Which means you need something flexible there. Extremely flexible that can adapt. You need something flexible because you don't know. The second thing, this is open to other developers. This is going to be given to enterprises, because since you don't know what's the edge use case, you're going to give them edge computing capabilities, and you're going to ask industry verticals, developers, okay, here, I can give you a low latency, something which is close to the edge. Please, this is my edge computing location. Please develop the killer app for me. You can find it out, okay? We let the market find out, okay? This means that, in fact, this has to be attractive to developers. And this has to be a generic, let's say, a cloud computing platform that is already attractive to developers, and that ideally already has a very extensive ecosystem in the IT world. And again, an edge application, B2B edge application, is not just going to live at the edge. It's just the edge part that's at the edge. But you know, a B2B app is going to have, you know, a control center, which is very likely to be in a public cloud, for example, like, you know, an AWS cloud, the Google cloud, or maybe in a private data center. But this part of the application that's sitting at the edge is just a component of a larger application. So as a developer, I don't want to have to use specific tools because, you know, my application happens to sit at the edge. I want to use exactly the same tools. Maybe I use on Google Cloud, on AWS, or I use in my private data center. Otherwise, it's too difficult. I don't want to learn new tools. So here, the ecosystem, the existing, let's say, ecosystem is really paramount to be able to attract these developers that are going to invent, you know, the B2B edge use cases of the future. So here I'm going just to illustrate, you know, such kind of platform, you know, with the platform that we have developed. So it's called, and Ben already mentioned it. So we have OpenShift. It's called OpenShift Container Platform. It's a container platform based on Kubernetes. You can deploy it already on public clouds and private data center. It's widely used in IT. But what we have done over the last couple of, let's say, 2-3 years is to adapt it for the edge workloads, you know, including the radio access workloads. I'm not going to spend a lot of time. The only important things here is that one of the things that we had to do is to reduce the footprint. It can run in 3 servers, can run even in a single server. That's what you see on the lower part of this slide. And again, at the edge, the challenge is scale. So we have also added, you know, a number of management products which are on the top. And the main purpose of these products is to be able to manage, you know, hundreds, if not thousands, of these Kubernetes edge clusters. So that's something that we have done over the last couple of years. But again, such a platform is of no value if it doesn't have, you know, a very attractive ecosystem. The value of any platform is its ecosystem. So I'm just going, and this brings me back to the topic of this session, which is the collaboration, the industry collaboration with the other telco players, the other telco industry players. So what we have done also over the last, you know, 2-3 years, we have worked with many, let's say, ISVs, network equipment providers, you know, some of the kind of more traditional ones, like Ericsson, you know, Nokia, Samsung, NEC, but also some of the, let's say, more newer players, like Mavnir, Altiostar, which is now part of Rakuten Symphony. And we have worked with all of these industry players to make sure that, you know, all the workloads that I talked about, and this slide is just focused on the networking workloads, okay, so the Open RAN, vRAN, Cloud RAN workloads, as well as on the mobile core workloads that you also have in this near edge. And we have worked with them, we have listened to them, we had to modify our platform so that they can run our workloads on our platform. And the main goal here is, you know, what's on the red box on top, is we want to give telco service provider to choose, you know, to have the freedom to choose whichever workload they deem best for their requirements. Okay, that goes back, you know, to the overall goal of Open RAN, which is to open up the ecosystem and, you know, to have also to be able to have a best of breed choice, you know, of workloads. So we have worked, you know, with all of these players, the traditional ones as well as the more, you know, newer ones, to make sure that our workload works. And okay, there are a couple of links that you cannot click on, but which are freely publicly available, where you can see all of these players have said, yes, we have tested our, let's say, workload on this platform, both mobile core and RAN workload. And now let's come to the last workload, because that's the important one for monetization for the platform, which is in fact edge computing. Here again, I just want to highlight, some of the key features here. We very much believe that AI, ML at the edge, the processing of data, this is the differentiator where, a telco has a big role to play. And the competition here, it's very clear. The competition for public cloud, let's say for telcos here, are public cloud providers. It's the AWS, the Googles, etc. Because we are in the same domain. It's about, offering cloud computing to application developers to have interesting B2B use cases. But the unique advantage of a telco is that, he has this real estate at the edge, at the far edge. And for those use cases where the local processing of data, here, for example, I just think, for example, video analytics. Video analytics, you analyze a lot of video streams from different cameras, and it's just not, it's just not economically viable to centralize this in a public cloud data center, because there's so many cameras potentially that you can have. So, in my personal opinion, video analytics is one of the use cases. It has to be local. It has to be at the edge. And the opportunity, for example, for telcos is to democratize the access to video analytics, because they can do it on behalf of smaller enterprises, putting these kind of application in edge data centers. And then they can offer this type of services. And this is, it's very difficult for a big public cloud service provider to do. It's not in their DNA to manage, a lot of distributed cloud. In fact, we are talking to some of the public cloud service providers who have these capabilities. They have now edge locations, different names. And in fact, in their heart, they don't want to do that. In one of the projects, we found another way to do it in a centralized way. Say, no, it's better to put it in our public cloud. Okay? So there's really an opportunity for, let's say, a telco service provider to enter the edge computing, the cloud computing space through the edge. But they must seize that opportunity. So therefore, I have highlighted, the importance of supporting AI/ML with things like GPUs. So that's one of the very important things. And the last thing, is the extensive developer tools, which we have. And the last one, in fact, is the IT ecosystem. So this is just an illustration of the platform that we are proposing for the edge. It's already well established in the IT world. So there are already many application components. You see a lot of logos on these slides, which are already being used in the IT world for this type of platform. And then it's just a matter of reusing the same components at the edge. But again, we think the IT ecosystem for the monetization of B2B is one of the key things. And lastly, when we finish, let's say, on the openness, I'd just like to highlight that as we try to open, the radio access network, we have been in this game of open for a very long time. I'd just like to highlight that, in fact, last year we acquired a company to do cloud native security. And we have one of the things that we always do in our company that kind of makes us different. We open source everything. So every single, let's say, product that we put in this platform, it's open sourced. And in fact, everybody in the industry can collaborate, can improve it, and can work with us on improving this product. So this is just a press release where we show that we have, we have open source some proprietary technology that we acquired last year. And again, this is at the heart of Red Hat. We believe in the power of openness, of sharing, on working together on a common problem and finding a solution. Thank you.
It was said very clearly by Mr. Shyam, and by explaining the challenges of Open RAN, and it's not something, there are a lot of promises around Open RAN and what it brings and there are some high reality, everything is mixed, so different people have different perceptions. As he rightly pointed out, it's not that you take a existing workload like DU, put it on a COT server and it works on day one, right? So it's not that easy. So there are a lot of things that need to be made to get the DU working on a real-time system, which is on the COT server, which is not it meant for, right? I mean, these systems are meant for some non-real-time applications, at least till now. So going forward, these systems are also coming up with and taking care of the real-time requirements of Open RAN kind of network functions, including the DU and other things. So let me move to the. Okay. So I'll just briefly talk about Mavenir and where we are with respect to Open RAN systems, and then I'll briefly talk about the evolution. I will touch myself keep myself towards the RAN DU and CU nodes, as these are the most critical items which are going to be real-time oriented, and they demand more on the compute hardware. And how the hardware ecosystem is evolving and how that is helping the Open RAN to become a reality. So that part I'll cover. And then the Open RAN architecture options. Okay. So as Mr. Shami has put, so the system integrator plays a bigger role, and that's one of the biggest challenges, because unlike a traditional vendor who brings in everything right from radio all the way to the core and then brings up the network by themselves, the Open RAN is not like that. So you have a radio coming from one vendor, RAN coming from another vendor, core coming from another vendor, the entire hardware platform coming from different vendors. So to make all of these work is not a child's play, right? So Mavenir has been a key player in the system integrator and has an experience in all these facets, right from core, which we are expert at for years together. So we have experience in terms of bringing the core, IMS, RCS, and those kind of services into the cloud far well in advance, much earlier than most of the other players. So we have experience in terms of bringing the network functions to the cloud, so that helped us. The second thing is we also have complete RAN portfolio, including CU, DU, and we are also getting into the RU portfolio. So we will be having, I have another slide for the radio portfolio that we have. So we have big developers. So 5,000 plus skilled resources are there with us, and the R&D engineers are mainly based out of Bangalore, India, and we have presence in Sweden, US, and other countries. So majority of the development happens based out of India. So coming to the, I think many of you might be knowing about our RAN play and the core side of the play. So when it comes to the open radios, yes, we are there as well. So we have radio portfolios right from smaller 44R, 2T2R kind of radios, all the way to the massive MIMO 6040R kind of radios, including the millimeter wave radios. And again, when we say we are also bringing radio, it doesn't mean that we will sell or we will restrict ourselves to say our RAN software will work only with our radio platform. So it's a mix and match. It is operator's choice. So if you want RAN from us and radio from anybody else, or the other way around, both are possible. And we have already started integrating our radio portfolio with one of the other DU vendors' portfolio. So it's already happening. And in the live network already, we have demonstrated that our RAN, DU, and CU can very well interoperate with a third-party radio, completely independent third-party radio vendor. And we are successful in terms of integrating so many radios. I think by now we have integrated more than 30 different variants of the radios, and at least from 10 different vendors, radio vendors. So all this was not happening in one day. So I mean, I remember 3 years before when I joined, so we were just starting on the Open RAN journey in terms of the radio integration. So the first radio took pretty long time. I mean, it's not that it happened on day one, right? So it took a really longer time because everyone was learning about what is the front hall interface and what are the nuances of that interface specifications. There were so many loose ends on the specification as well, so which required interworking with the radio vendors, discussions with the radio vendors, plugging the holes back into the specifications. So as you can see from version 2, just 3 years back, the front hall specifications in the Open RAN has gone to almost V7 and version 8 kind of specifications. So all this has been possible because of the active contributions, the way we have learned during the integration, and the feedback has gone into the specification. So all this is to say that, yes, it is not a child's play. It's not something that's going to happen on one day, but it is not impossible. So we can make it work. We can make the open interfaces work across different vendors without any problem, and we can introduce radios very quickly. So we are integrating radios almost in a weekly basis. So there are new radios getting integrated into our portfolio at that speed. Okay, so just briefly touching upon how the evolution has happened on primarily on the DU side. I mean, I would cover both CU and DU, but the major complexity is on the DU side. So if you see some of the things, it will be more focused towards the DU side. So it all started with the custom equipment, like from traditional vendors. It's a single box solution like an E-Node B, like in the LTE case. The first thing is to achieve is disaggregate them, differentiate the components which require real-timeness versus a lot of control and a lot of intelligence needed. So CU, DU was separated out, and then you have multiple vendors coming in with respect to the RAN and the RU, so which means the front hall is open. So that disaggregation helped in terms of bringing different vendors coming together. Then the next step is on the virtualization. So you have a single hardware, but how do you make sure that different network functions run on the same hardware without having to do extensive testing of all of them running as a single process or a single binary, right? Then came the private clouds. So with Kubernetes, we started integrating with container-based framework. So what it brought in is it brought the RAN nodes into the purview of IT infrastructure or the orchestration infrastructure, the automation infrastructure, which is already prevalent in other technology domains, which has been adopted into the RAN domain. So it has we started making use of those technologies inside. And then when it comes to the compute hardware, so the DU is not something that is going to be so friendly with just the software part. So there are some intensive applications which require a huge amount of signal processing capacity, which means you need to have some accelerators. So the first accelerator which came was the FEC, that is the forward error correction accelerators. So that offloaded the important and the heavy lifting of the decoder functionality mainly. Encoder is not that as complex, but still, because of the huge data rates in the downlink compared to the uplink, so you still need the FEC accelerators for both the downlink and uplink. Then came the inline accelerators, meaning the complete layer 1 is offloaded. So which means it frees up some of the CPU capacity for your L2, L3 applications, which means in a single server you can do much more than what you can do with layer 1 plus with the simple FEC accelerations. And the next step is towards a completely public cloud, where what is the need basically. So it also means that your network function like DU, which is time critical, should be agnostic of the hardware or the variations between the hardware. It has to be capable of running different CPU platforms. It has to be running in a completely containerized environment without requiring certain privileges. These are some of the bottlenecks that we have to unblock or remove as we moved along in the journey of cloudifying the complete RAN network. So, what does that bring? Going into public cloud also means that you no longer need a capex to get all this infrastructure. You go into an OpEx model where you rent the capacity, rent the compute capacity from the public cloud providers. Then comes the microservicing. So we are in the journey of microservicing the BDUs, where it also means that till today, if you look at the DU as a network function, it's always like a monolithic function, which means it cannot be scaled based on the capacity. So it's not microserviced like a CU, where you take different pieces of the network function, compile them into different containers, and as the capacity needed for a particular function, you increase the number of containers for that particular function. That's the advantage or the beauty of microservicing. So that will also be brought into the DU space. So which will allow us to truly scale up and down the capacity during the runtime by adding more and more hardware compute capacity as needed based on the traffic load in a given day. So what has driven the overall growth of the Open RAN and made it possible to bring it into the cloudification and also to bring the disaggregation and also go towards the edge? So there are two major areas of silicon development that has played a critical role. So one of them is on the layer 1 silicon, the other one is on the radio side. So on the layer 1 side, as we discussed just before, the forward direct correction is one of the initial ones which got accelerated into a special purpose silicon basis. So the initial ones were based on FPGAs, so which means it's power hungry and it requires a lot of effort to bring it on your own. And then later came the ASIC or eASIC oriented kind of platforms in the form of Mount Bryce, and then the inline accelerators which are coming up in the offing. So like as I have captured here in Marvell, Qualcomm, NVIDIA, everybody is coming up with their own inline accelerators which will also help us to have increased the capacity per server. So does this mean that we are no longer going to have layer 1 in software? No, it's not the case. Everything will coexist. So you will have cases where you will have everything running completely in software. You will have cases where L1 is running on software with FEC only accelerated into a chipset, or you can have a complete L1 offloaded to a card like Qualcomm card or the Marvell based cards. So how is this possible? I mean, how can one vendor take care of various options of layer 1? This is coming in because of the standardization that's happening in the in the ORAN community, where the layer 1 to layer 2 interface is also getting standardized in terms of inline accelerator APIs and in terms of how the interface between L1 and L2 will evolve. So SAF API is one of the standard specifications which will help us to disaggregate the layer 1 and layer 2 functions, which will allow any vendor to have a flexibility of using any layer 1 depending on the situation, depending on the capacity needs, depending on the type of DU, depending on the technology that you need. For example, millimeter wave or massive MIMO, where the capacity needs are huge, you can go in for inline accelerations. Whereas when the capacity needs are not as huge, so you can still serve with any simple FEC acceleration based solutions. The next driver is on the RU silicon. So on the RU side, if you see, the traditional radio vendors have either used their own custom ASIC or FPGAs like Intel's FPGA or Xilinx FPGAs, which consists of programmable logic plus some CPUs like ARM cores, few ARM cores inside. And then it became, slowly it started migrating towards integrating RF into the chipset, which means you can have CPU plus programmable logic plus radio frequent RF components like ADC, DAC, and the few of the analog components into the same chipset. And slowly we are getting into a phase where the CPU plus lo-fi plus RF is all coming in the form of a programmable chipset, not really the FPGA based versions, but if you look at that, some of the companies have solutions like for this radio side, which includes all these components. And eventually we will see the silicon extending towards the radio side, including the layer 1 as well. So there are possible architectures wherein you will see the complete layer 1 moving into the radio side, not just the low-fi. So that's probably the next step. As the bandwidth requirements increase, the front-haul capacity requirements also increase. So that will push that step as well. So just to give a picture of what happens and what are the different specifications and how different things have been evolving. And so what is helping us? First thing is 3GPP has defined the complete functionality in terms of different possible splits. So right from option 1 to option 8. So you can have one of the split, or you can have multiple splits in your RAN network. So for example, you can have option 2 and option 7, or you can have option 2 and option 8. So each of these provides a flexible way for any radio vendor to pick up and choose a particular component of interest and then develop only that, and expect them to work with a third-party component for the other portions of the RAN network. For example, if you see towards the right side, the option 8 split was predominant, and like a CPRI based interface, 2G, 3G, 4G radios were starting with CPRI based interfaces. Then came the option 7 interface. It got standardized. eCPRI was also there before, but it was not to the extent that it can be open interface. I mean, you can just plug and play. So what Open RAN ORAN specification group did is took the eCPRI as a specific base specification, filled the gaps in terms of specifying exactly how you want to configure, how you want to administer, how you want to send the signal in a particular format. So all those things were nailed down in the ORAN specification. That helped making this option 7 interface a completely open interface. So that that laid the way for integrating a third-party radio with any DU vendor using a completely specification-based open interface. So what's going to happen in the future? So can we look at option 6? So that's probably the next move, because as you see in the bottom, you can see that the distribution of the lower layer functions as you move from left to right, you see the latency requirements going up. And similarly, when you are centralizing the higher layer functions, the capacity requirements on the CU-DU interface goes up. So as you move from option 1 towards option 8, the interface speeds keep increasing. For example, in option 8, if for a 20 megahertz bandwidth, if you need X amount of bandwidth, when you come to 7.2, it becomes 60% or 50% of that capacity is what you need from an interface data rate perspective. But if you can move from option 7 to option 6, it could be 4x, 5x reduction in the bandwidth requirements on the front haul interface. But as you see, the millimeter wave already talks about 800 megahertz of bandwidth per site. So as the bandwidth increases, the bottleneck on that particular interface between the DU and RU is going to become a choking point, and that will pave the way for other splits like option 6 radio, wherein the complete phi is inside, which means that you are moving the interface towards the left and reducing the data rate that is required between the DU and the RU interface. So that's one of the directions things are moving towards. So how are the splits? So as we saw, these are the protocol stack layers, as you can see from the left, layer 3 all the way to the physical layer function in the right side. So you have the cloud at the DC, which is taking care of the centralized unit, and the DUs are typically, as of today, if you look at, there are multiple choices. It could be a cell site server, which is just catering to that particular site, or in the next slide we will see other options. So the RRH is taking care of the low-fi and the RF. So as we move towards the next generation of the architectures, so the edge cloud comes into play, wherein you are going to centralize, or in a smaller scale, not at the scale of the CU units, But at a smaller scale, you're going to centralize the DU functionalities to take care of, to take advantage of the pooling gains. For every site, every cell is not going to be 100% loaded at every time, and different sites have peaking throughput traffic at different times, which means the moment you get the DUs aggregated into one particular location, even for 5 sites, even for 10 sites, if you can aggregate them into one location, you take advantage of the pooling gains. The total hardware compute capacity can be reduced significantly. So that is possible because the option 7 interface, as per the specification, it brought in up to 160 microseconds of latency as between these two nodes, which means in a direct fiber, you can go as high as 30 kilometers of distance between the DU and the RU. So 30-kilometer radius in an urban environment could mean a lot of sites within the vicinity of that particular distance. So as we discussed, the 6G or the very high advanced large bandwidth applications might get into this kind of architecture, wherein the radio or the hardware box that is sitting in the tower is swallowing in the hi-fi application as well, apart from the low-fi. So that goes into the kind of an accelerator-based mode, and the rest of the things can get into the centralized cloud, because the interface now being between MAC and hi-fi, it is not as delay sensitive compared to the hi-fi to low-fi. So hi-fi to low-fi, the delay requirements are in the order of 160 microseconds, which is what is defined by the ORAN specification as of today. Whereas in the option 6, you can go as high as 500 microseconds, even to 1 millisecond if you are able to tolerate some of the latency on the ping latencies and the call setup latencies and other things. So what does it help us? It helps us to basically centralize more and more compute. Everything can get into the public cloud, everything can get into the pooled capacity rather than dedicating capacity per site and leaving them idle for most part of the day where the traffic is not at its peak. So there's another area which is coming up, which is neither in this, which fits into none of those 3 architectural options, is the enterprise solution, wherein everything is sitting in one particular location. So you have the CU, DU, RU, core, everything is part of the same enterprise area or a building or a campus. So in those cases, it's not just the RAN, it is also the applications on top of the RAN, which is also important. So we have demonstrated kind of solutions wherein the NVIDIA kind of solutions where it also has a layer 1 capability. It can also provide artificial intelligence capabilities. So what we can make use of that is you run the modem pipe using its layer 1 capabilities, and once the pipe is given, the devices connect through the 5G radio technology to the server, and the server also hosts core, and on top of the core you have the applications running on top of it. I think I'll conclude. Thank you. Thanks for your patient listening.
About right now the learning and experience that WIT Wind River has from deployment of the past 2 years, starting from the first ORAN 5G network in the world. Okay, with a tier 1 carrier, and since then actually we already have 4 commercial deployments in the world. The largest of them, it's over tens of thousands of sites. Myself, I lead the solution engineering and architecture team, so basically the team that work with the service provider from the design phase of the network, integration with the ecosystem that the service provider select, all the way to exit of the FOA and the scale deployment. So let's see. Okay. So first of all, maybe for some of you, you don't know Wind River. I tend to say it's one of the best kept secrets in the industry. Okay. If you operate today a 3G network, a 4G network, you don't know, but you use Wind River. Pretty much every purpose-built equipment that you have in your network today, it's using Wind River operating system. So telco, it's not new to us. So whether you use an Ericsson or Nokia or Huawei or Cisco or Juniper, it all uses Wind River. Furthermore, if I take it specifically even to the Indian market, the entire military aerospace industry of the India market is using Wind River operating system. So all your weapon system, everything, it's relying on Wind River system. Okay, so we are 40 years in business, actually over 40 years now, okay, and we're pretty much in the wireless network since the initial days of 2G. If we look at the deployment that we have, below you see the service provider that we have commercial deployment with, all our public information. The biggest one of them, this is the first in the world 5G O-RAN network, it's Verizon. Okay, but since then we also deployed at Vodafone, at KDDI, at SoftBank, all commercial 5G O-RAN networks. If you look at the type of O-RAN networks that basically are deployed using Wind River, so you can see it's ranging from a narrow band in the macro network to the C-band, all the way to small cell and private 5G. So we basically have commercial deployment at scale with all those type of spectrums and types of solutions. Those are just quotes from the two big tier one operator that selected Wind River. And again, we're talking about commercial. We're not talking, there was a lot of discussion about let's get out of the POC phase into the commercial. We're way past this. We're for 2 years deploying commercial networks, 5G O-RAN networks. I'll get to the architecture in a second. Pretty much if you look at Verizon today, the deployment that we have, and this is a public quote, CapEx and OpEx, it's equivalent to what they have in the non-virtualized network in the prior to it. So KPI, we basically have 5G services running full year without any disruption. So we're not talking about 6.9, we're talking way beyond 6.9, pretty much zero downtime. So first of all, let's look at the high-level architecture, again, of the commercial disaggregated O-RAN solution. Okay, I'm not talking about an ecosystem where you have a lot of nice logos, but really I'm talking about one that are commercially deployed. So you can see from the application side, from the VDU, from the VCU side, okay, the vendors that we have commercial deployment. In the middle, it's the Wind River Cloud solutions from the cloud platform, the management and the analytics solutions that are used for service assurance, for closed loop automation, and at the bottom, the different hardware components. So whether it's commercial off-the-shelf servers from HP or from Dell, again, those are all commercially deployed. For example, an HP DL110 or a Dell XR11, again, all deployed at commercial scale. From an acceleration perspective, again, you heard about a lot of acceleration, but today if I'm looking at the RAN network in commercial deployment, it's pretty much an Intel Mont Bryce. There was a discussion about the FPGA. The FPGA was the starting point, basically just to, let's say, see the viability. But at the commercial scale, an FPGA, obviously, it's too heavy, both on cost and power, and you're going with an EA6 solution. Now, there is other solution coming into the market. There was a mentioning of NVIDIA, mentioning of Marvell, mentioning of Qualcomm. Some of them are targeting different parts of the 5G radio network, like private 5G versus a macro, okay? But if you're looking at commercial deployed, it's pretty much the Intel AC100, also known as codename Mont Bryce. So let's look at the architecture. Now, when I'm talking O-RAN, I'm talking about really a 7.2 split, okay? 2.7 split, which meaning just a CU, there is nothing new about it, and really there is not a lot of challenges in it. Okay, we're talking about a 7.2 split, basically where you deploy the VDU, okay, at the cell site, in the case of a distributed RAN, or you're deploying it in a bigger site, but still what you call a far edge, small site, in what you call a class 2 pooling, or known also as a CRAN. So if we look at the typical operator, they usually have a 4G network already deployed with a core that it's virtualized. Okay, in some cases, they may even have the CU running and virtualized. It's really building the whole far edge where you are going to deploy the VDU. And in some cases, also the CU, in some cases, the UPF, depend for what type of application. So first it starts by most of the operator basically will have an OpenStack-based, VM-based solution in the core. So expanding this into adding Kubernetes, cloud-native capability. This is usually to run the 5GSA core components, for example. Okay? And from there, starting to build the far edge. Now, really, if I'm looking at especially at what I call a brownfield deployment, so an operator that already have a 4G, 3G network, usually they will start with what you call a DRAM type of deployment. So a cell site where you put an edge data center, and when I say an edge data center, a single node server where you basically will run your VDU and in some case VDU and VCU on this single node. Okay, completely distributed cloud with a distributed control plane. You're going to deploy it from the central, from the regional data center. This is an ORAN terminology. Some will call it an edge data center. And you're going to deploy it the far edge data center and deploy the workload and run it on the single server. Then expanding to those sites that basically will carry multiple workloads. For example, dual band, for example, will carry MEC applications, UPF, okay? And also in some cases, those CRN site, for example, will be used for a class 2 pooling, okay? Now, how you start, if I look at the reflection at the 4 operators that we are already in commercial deployment, they start with the DRAM and then they build up the CRAN. Simply because the way their transport network is laid, it's in such a way that it supports a DRAM deployment. For a CRAN, for a class 2 pooling, for example, you need to have a lot of fiber in the ground. You need to have it in such a way that basically you can create a baseband pooling, and technology-wise, still evolving together. But really, what we're focusing today, beyond the scale deployment of DRAM with operator, we're actually starting a class 2 pooling deployment today with some of the big operators. So if I'm looking at the journey, and really it's depending on the operator, but like I said, we started 2 years ago with the first carrier. It was Verizon. It's publicly announced. Again, tens of thousands of sites already in commercial deployment. The journey started, and it's the same really with every operator. It's first start with what we call the lab readiness. Okay, so basically preparing the infrastructure, designing the infrastructure, testing it with the network planning and the maintenance engineering team at the operator. Then bringing the workload and basically testing the workload, okay, and the complete integration to make sure everything works fine. From there, moving into the FOA phase. So the FOA phase, it's basically commercial deployment at small scale. We're talking a few sites, a few hundreds of sites, okay, and during this phase, basically working all the details and the learnings to be able to scale to a commercial large-scale deployment. And then moving into the phase of the large-scale deployment. When you say large-scale deployment, what does it mean? Today, we're deploying at a rate of 1,000 sites per week. So basically 1,000 geographically distributed sites per week. And this is really where it's going to lead me into the learnings that we have. Because there are a lot of mentioning about PTP, for example, about low latency, all those type of things. Those are all great. Those are table stakes. Those are things that we had many years ago. Okay, those are the things that when Verizon, for example, selected us, obviously those were the reasons. But I can tell you there is a lot of learning that came because those are great. It's when you start to deploy at scales, you're not deploying 1 data center, 7 data center like a core. So if you look at the tier 1 operator, there will be handful. You can count it on 1 or 2 hands number of core sites. Yes, the data center may be a lot of nodes. But you basically have a technician that goes, install the data center. It's really in one location. When you're deploying at a tier 1 operator, and I'm not talking about even India, where the numbers are 4 or 5 times bigger than like a Verizon or AT&T, for example, or even a Vodafone. Okay, in Europe, you're talking about hundreds of thousands of sites. So the meaning of scale is totally different. They are geographically distributed sites. Okay, so automation become a key important thing. Okay, things need to just work. If they don't work, if you basically come and install a site and it doesn't come up, okay, it's a problem. It's a problem if you need to send a technician down. It's a problem when you're trying to basically deploy 1,000 sites in a week, and for example, 30% of them doesn't come up. Okay, what if 50% of them doesn't come up? Those are really the things that you need to think when you're deploying an O-RAN network and deploying it at scale. It's not just the table stick of performance and stuff. That those are obviously, without this, you can't even run a workload like a VDU. So I'm going to walk through a couple of the key learnings. We're limited in time here. I can spend hours and hours and days actually going through everything that we learned and also the different solutions, but I'm going to touch on the highlight, the key ones here. So first of all, the requirement of starting in the deployment and before as you test everything and you start to deploy, of basically alignment of everything. You're talking about a disaggregated, okay? Now, making sure that people get out with the right message. It is complex, but there is solutions and it's been done. And it's actually not as complex as it sounds, okay? It's just a different mindset because today in the traditional 4G, you basically get the whole solution from one vendor. So many of those things is things that you don't see. They're already been handled, okay? Those are the type of things that when you go to a disaggregated solution, you need to be aware and you need to be prepared ahead of time. Working with someone that actually did it at scale will save you and reduce your risk. It will save you a lot of time and reduce the risk dramatically. So if you're looking, for example, commercial off-the-shelf server, okay, the hardware that comes with different NIC, different accelerator, and then you're looking at the VDU. There need to be an alignment between, for example, the drivers, the firmware, okay? The server may be stacked in the warehouse at a certain time, loaded with a certain firmware on it, okay, and shipped to the site and arrive to the site weeks or months later, okay? And as you roll your network over time, you have more and more sites. So, but you purchased maybe all the servers at one shot. So you got a lot of, 10,000, 20,000 servers, okay? So you get to the site and, things are not aligned. It's enough that the firmware inside the accelerator, it's not the right version. The video is not going to work. The platform needs to have the capability to be able to audit this, to be able to have basically a seed template that looks and say, okay, this is the type of firmware that the NIC need to have. This is the type of firmware that the accelerator need to have based on what the video requirements to make sure everything is there. So when the server is powered up, basically to audit it and say, yes, it's there. No, it's not there. Go and program it and going and programming it. This is the key important things. And during the preparation for the FOA, we work on all those things, creating when I'm saying the design, the seed template, everything to define all those things and making sure that they are happening in fully automated way when you deploy. Next thing, it's basically streamlining this validation, streamlining the working with basically the vendors. Going into basically how do you install at scale? Okay, we're not talking about installing a single site, not talking about even installing 50 sites. Okay, we're talking about thousands of sites in one shot, in parallel. Okay, so it's a whole different ball game. Okay, so those are very critical things. It's for example, the installation of the site will be done usually on the OEM network. Okay, so using the management network, it's tend to be the, let's say, least reliable one. It's limited in bandwidth. It's limited in bandwidth, okay, and usually there will be a lot of issues. So how do you deal with those? Okay, how do you make sure that when a site is installed, indeed it has everything that need to be there and ready to receive the workload? Because otherwise, okay, you load the workload and things will not work. From there, it goes into manage at scale. Okay, how do you manage the upgrades, the updates? Okay, going from one platform version to the next platform version. Okay, how do you manage deployment of a single site? A single site, single server, okay, it basically, doesn't have high availability. So you need to do canary type of deployment. So radio overlap. So you group basically multiple single server sites, okay, in groups, and you say, okay, the green group, for example, will get updated first, and the red group will take over for the green group from basically radio overlap. Once these get deployed, you switch them. This all need to be done in an automated way, okay? And it need to be done in a way that you basically, in one maintenance window, you can upgrade all the sites. You're talking thousands of sites. So if you're looking at a traditional radio network today, you pick your favorite vendor. When you apply an update or you apply a patch, okay, you apply 15,000 sites in one shot, in one maintenance window, okay? when you do an upgrade of a whole complete cloud platform, you basically need to do it in the same way. Okay? You can't go and say, okay, I'm going to push this. And then once everything is staged, during one maintenance window, it's going to upgrade all those sub-clouds, thousands of sub-clouds all at once. So thank you very much. I'm going to conclude. I'm already got twice that I need to finish. I will be happy to speak with anyone after if you want more information. Thanks.
Good afternoon, guys. I know I'm the second last before the lunch, so I'll try to be very quick because I think we are running already over time. So I'll try to be short and quick. My name is Arif Khan, and I'm the founder and CEO of CoreEdge. Before starting this venture, I worked with Ericsson almost 10 years. There, the last position which I was holding was head of cloud PDU. And this is the time I was talking about 2010. Just give me a second. Yeah, 2010, when the whole box business was converging to the cloud-based architecture. And we were the one who were doing this transformation, a lot of good learning, and it was not easy. Even onboarding Ericsson application on Ericsson cloud was so much of pain. And that's where I thought, what will be the situation at operator side when the things are coming from different vendors. And that's where I started a company called Vor-Ir in Sweden, which was only focusing on interoperability issues on cloud testing. And that company is still operational. We are working with some of the top tier 1 telcos like Deutsche Telekom, Singtel. But something interesting happened, and that's the time, early 2020, when I started looking. Of course, COVID was there, so got a lot of time to read about it. So edge computing was something which is really very close to my heart because a lot of opportunity. When I was reading around Industry 4.0 or 5G, edge computing became the critical, integral part of the whole architecture. And that's why I was motivated and started this company, CoreEdge, with the focusing. And you can pretty much see that we are trying to bridge the gap between enterprise and telco. So for us, even ORAN is one of the app like any other application. So that's the background about CoreEdge. Yeah, we are pretty much young company, but already working with some of the top tier 1 telcos outside India, even some government agencies and cloud service provider. So even from our revenue, we are pretty much 50% revenue coming from telcos and 50% coming from enterprise. Right now, given that the conference is all about Open RAN, so one of the and I think our fellow speakers and even in the morning sessions, we learned a lot around Open RAN, the benefits, the challenges which we are seeing on the total cost of ownership. Now, what I will bring a different perspective on the table, because now we all know that it works, right? We have done trials, we have seen POCs. Now we need to build this a production-ready scale in the operations. And that's where some of the key consideration which I wanted to bring on the table, so that when you guys define or decide your architecture, you more like a food for thoughts. So right now, 4 components which you really look very carefully when you are driving your Open RAN strategy is first, selecting your hardware vendor. And hardware, we always say that, yeah, it's out of the box, so it should run on any hardware, right? Yes, it should run on any x86 or any standard ARM or any architecture. But then RAN has a specific need from the cloud or from the edge, which needs certain accelerators from the hardwares, right? It can be DPDK or SmartNIC or anything. So you need to really carefully when you are selecting your hardware with these accelerators. So that's the one perspective which you should spend time, absolutely. Second is cloud native architecture. And this, even from Ericsson side, which we have seen, even now, what has happened, people done this transformation from box to virtual machine. And now suddenly when telcos, some of the innovative telcos, they said, okay, we want to go CNF. And what they done, they have just put all the, everything what was there in the virtual machine into containers, and this is good to go. But that's not really solved the purpose. You need to think more as a cloud native architecture. You need to think RAN as a function of, or jointly you see that it's a combination of 10 different microservice architecture, because then only you can take an advantage. Wherever the need is, you can spin off certain micro services, and that's how you can get this high density and a lot of other advantages which cloud native is claiming on. So that's another perspective which you have to really evaluate when you are selecting vendors. Third is management and orchestration, because now we are talking about not couple of data centers, thousands and thousands of edge sites where your workload will be, so automation becomes the key. No human can manage this kind of, like just imagine if I have to do 30,000 edge site and I have to upgrade Kubernetes 1.12 to 1.13, manually it's insane. So the automation, management and orchestration piece is very key. The SMO, and this is very much in specifically written also in ORAN standardization, the SMO part of it, and that's where even CoreEdge is playing a play. So we are into this SMO piece. Last, that you should have a flexibility that you can deploy virtualized function, which you can add on as a value add on top of RAN function, like ML and other things. Then you can create more revenue stream and become much more smarter. So these are very high level components which you have to really look. Some of the consideration when you are building edge sites, right? So one thing is, with cloud, we are used to manage tens and thousands of servers under one cloud. Now we are talking about managing tens and thousands of clouds itself. So it's a different, it's much more complex than what we have seen in the whole transformation of NFV, what the challenges which we have seen. And these edge sites, of course, they are in numbers very huge, but it's a very, very capex intensive, and you are not going to build per edge site for per application. No operator will do this, that, okay, I'm only for ORAN, I'm going to build this particular edge site. You need to think when you are deciding your architecture that a lot of other application, whether it is IoT gateways or analytics or much more things will be done on this edge sites. So that is the key consideration when you were defining your strategy. Of course, there are a lot of things because with microservice architecture, there is a very dynamic changes like the auto configuration of firewall, those service mesh. So while designing your architecture, you need to be careful on those consideration as well. Right? One very, very simple example I can give you, that right now Kubernetes provide only the single interface on the pod, right? And most of the telco application, they need secondary interface because of obvious reasons of throughput and other requirement. And the moment we deploy in production, of course in lab it is fine because I can give an IP to the secondary interface and I can communicate and everything works fine. But in the production, when you are dealing with thousands and thousands of edge sites, these IP allocation cannot work. The service discovery should happen automatically on this secondary interface. And the moment the secondary interface comes into the picture, the service mesh and other technology like Istio which are present, you cannot really assign service discovery, right? So there are solutions, and of course, industry right now, I'm clearly seeing that some players are bringing their own CNI, but again, that's also one kind of a vendor lock-in for me. Some are solving through orchestration where they are giving a service discovery. So it's a choice which you need to make, right? So last but not least is operational requirements, because you have a team which is already running it. Even brownfield operators or even a greenfield operators, with this so much of technology coming into picture where we are talking about multi-cloud, even within multi-clouds, we are talking about using hyperscalers. Maybe it can be AWS, Google or anybody else, along with my on-prem edge solution. So the operational challenges are going to be huge. So how do you manage it? How do you train your existing staff to run those shows? So those are the some more consideration which you need to really look on. Challenges, and which we have already observed working with some of the tier 1 telcos, or even many telcos across the world. They have actually implemented ORAN and even virtualized RAN, cloud RAN, and even legacy RAN, and at the end they are having island of technology. Even with NFV, we can clearly see that within operators we have 7, 8 clouds running, and which is very much tuned for specific application. So that will not really give you a benefit of total cost of ownership reduction. So in a way, when you define or decide, you don't need to build an edge site or a cloud which is best for a particular application. You should think of building an edge site or a cloud which is good enough for my all application. Okay. Operational complexity, and that's where I say that most tough part of any telco is that running it in a production at this kind of a scale. So you need to really think on those lines. What we propose, and that's what we have been advocating from quite some time now, that telco should opt more as an intent-based orchestration. Because even for ORAN, even for developers who will be building a lot of these 5G application, they don't really an expert over infrastructure, right? They know what their application need. So as an intent, what I mean is, I can just clearly define that I need this much of latency between this and this A and B microservices, and all the abstraction happen, and the orchestrator which is there can take care of it. So the intent-based orchestration is what you should really look on, where you define your intent once and then you deploy it on dev stage or even production. Cloud Compass, which is our product, right now it does the whole SMO piece as per the ORAN compliance. We have implemented O1, O2, and even A1 interfaces which are there in ORAN standardization. And within Cloud Compass, it's take care of your lifecycle management of infrastructure. That means your edge sites itself, even the lifecycle management of your application. So if you certain application like ORAN, if it comes and you have to do an upgrade over 30,000 edge site, you can pretty much do it. So yeah, I think this is what I wanted to convey, and I think I did a good job in keeping the time. So yeah, thank you guys.
So good afternoon, everyone. So I think I am the last one between you and your food. So probably I will try to make as crisp as possible. Even though the topic is a bit technical, but I will try to make it as simple as possible. So from the morning, in each speaker's discussion, one thing is very common, and everyone has highlighted the importance of AI and ML. And everybody is taking AI and ML in a different perspective. But if I see what is AI ML in a layman term, so if we see AI ML is like a algorithm or logic which takes some input or prior input and do some decision out of it. But how this AI ML algorithm will learn, and what is the learning procedure or methodology. So this is the topic of discussion, how the AI ML algorithm can be applied in a ORAN architecture or in a wireless architecture itself. So if we see from a 5G perspective, 5G is designed to solve different type of use cases, and the use cases are completely different from the requirement perspective. For example, it want to serve EMBB, EMTC or URLC. So what we want high data rate, but at the same side, we also want that the latency should be as much minimal as possible. And along with that, we want multiple devices to be connected with the same network. All three different requirements need to be solved by a single architecture or a network. So what will help what it will give is that even though we are doing a single network, we want the network should be very much flexible, efficient, scalable and programmable. All sounds good, but what it is in return is happening is that it will adding the complication in the network. The network is getting complicated day by day. So we are having 2000 plus parameters and configurations which are there for specifically for NR5G to make it scalable in different dimensions. Want to solve the EMBB use case, URLC use case, we need to configure the system in a different manner. So overall, if I say the complexity has increased. Now, if we see how the AI and ML can help here, we can see a different paradigm of use cases which are there, which can be solved by AI ML. Right from network planning, ratio resource management, mobility, power control. So everybody has its own problem and trying to solve it by their own AI ML use cases in their environment. We are looking for a specific requirement from a beam management perspective. So probably I will highlight the problem first and then probably we'll see how the federated learning can help here. So in a normal LT, the initial synchronization happens in an omnidirectional manner. So the synchronization signal like PSS, SSS is transmitted all across the cell. But what happens in NR5G is that since we are using a millimeter wave, the initial synchronization is also beam formed. So what is ultimately is happening is that if a UE wants to latch to a network, it has to first of all latch all the beams first, and then from that beam it needs to extract the PSS, SSS information. So in 5G terminology we call it as SSB. So what in return happen is that in NR5G, first of all we need to select the beam and then we need to get the signal out of it. So ultimately what is going to happen is that it is increasing the time for getting a signal when we switch on our mobile phone. So for example, when we switch on our mobile phone, the time taken to latch to a network will be going to impact it because this new additional procedure has been introduced. 3GPP has given a full procedure how to use the initial cell selection procedure, but how to optimize it or how to minimize the time duration, that is an open problem, and it is a problem which is there in the field when the 5G is going to deploy. So coming to the learning procedures, so there is one way. Let's say we have different entities, different users, and they have their own data. And we want to learn, the AI/ML algorithm wants to learn this information. And what it has to do, it has to send all its data to a centralized entity. This is a typical case where the problems like computer vision, in that they solve this problem. They send all the information to all the images to a centralized entity. They will learn out of it and then they will predict what is the best model, fine tune the model and deploy it. But things are a little bit different in the wireless domain because the data is not centralized. If there are different entities, it has to send all the information to a centralized place. What it will going to happen, it will additionally add the overload. So there are information which is needed for communication, but on top of that, we need additional communication of the data. What it is going to have in return is that use cases like URLC, where we are already in a very tight schedule of tight requirements from the time perspective, this additional delay will going to hamper the overall performance of the AI/ML algorithm. So, and also if we are sending the data, definitely the privacy will be a concern out of it. So if I look in a totality, this learning procedure which is good for other applications might not be a good fit for a wireless domain. So to handle this type of, or basically to handle this type of challenge, there is a altogether learning mechanism which is called a federated learning. And Google has done a very wonderful job to investigate or identify this type of learning. Basically, they use this, if you have seen in a Google keyboard, when you type something, it will give you some auto-suggestion. So this algorithm runs behind their learning algorithm where they do not want to share the actual data, but they want to learn from different users. Every user is typing in a different way. It wants to learn the grammatical things, also learn the patterns and information like that. So what ultimately they are doing is that instead of sending all the data to a centralized entity, what they propose is that let's a learning model runs on an individual entity. And this entity will learn from the local data itself. Once it will learn the data, information from the local data, it will send the learned model to a centralized entity. So for in case where within the example there are 3 entities, and 3 entities having its own kind of data. What is happening here is that the model is learning in the individual device, and the learned information will be sent to the aggregated place, and where it can combine all the learnings out of it. So what we have done eventually is that we are taking the information from a local place and only sending the learned information. So ultimately we have saved all the data transmission that need to be done from one entity to a centralized entity. We are sending the learned model out of it. So just taken a very simplest representation. So the model is, each device is learning its own model, and after learning it, it's sending its own weights. The global entity which is there, it is seeing the information from all the different informations which is coming from different entities. And finally, it is doing an aggregation on top of that and taking a global perspective of the information. So each device is learning whatever the information is accessible to that device, but the global entity is looking from a totality perspective and doing a judgment based on that, what will be the overall learning when we take the information from individual users. And this process keeps on continue till the time that we get a considerable good performance. So another interesting thing is that in wireless environment, so once we learn something, it is not necessarily true that the learning which we have right now will be suitable after 1 hour. It can be an interference, it can be a noise, it can be a different modeling itself. And specifically, once we move to the millimeter wave, it is very sensitive to the environment condition. So ultimately what we want is that the learning should be continuous. And this is the interesting thing which the global learning which is there. So it will keep learning from individual modules, and then it will combine all the learnings together so that it will keep changing itself or adapt itself based on the variation in the input. Now mapping it to the specific ORAN use cases. So taken a specific use case where the CU, DU or the entity is there in the edge cloud, however the RIC is on the regional cloud. So if we want to share or want to train anything on the RIC side, as in the previous presentation it is mentioned that the RIC is the key controller for the learning perspective. So ultimately what is needed is that we need to send the information from the edge cloud to the regional cloud. And by federated learning we want to avoid this specific challenge. So we won't send the actual data, we will send a learning model. So if we specifically go to a specific use case which is highlighted here, so things look, the infrastructure or the architecture of the learning looks like this. So in the lower part of the figure there is a ORAN infrastructure. So it can be an ORAN node depending upon the use case, it can be a CU or DU or RU. And what is happening is that the local model is running on the individual entity, and what it is doing, it is getting the data from that specific node, maybe it can be a CU or DU, and it is learning throughout this local data. And whatever it has learned, it is sending to the RIC. And now what RIC is doing is that it is have a perspective from all the nodes, and what it will do a kind of averaging of all the learned parameters. So RIC will try to do a performance evaluation on the global model, and it will check whether the performance is sufficient or appropriate for the current deployment. Based on the validation, it will check, okay, if the performance is meeting the benchmark requirement, it will send the global model back to the individual nodes, another through a E2 interface. And this loop keeps on going in a runtime environment. Every time we have some data or there is an information update in the data side, it will map to a model from a local model, and the local model will learn out of it, and it will send the information to the global averaging model. Okay, so coming to the problem which I want to raise in the initial beam selection. So what we want to inform that the beam which we want to predict should be as minimum as possible. So if I can reduce the transmission beams, ultimately what is going to happen is, in this example, there are two transmit beams and two receive beams. So ultimately, when I want to have a cell selection, I need to track the 4 beam combination to latch to a specific beam. Ultimately, what I want, if a machine learning algorithm can reduce the number of transmitted beams, let's say instead of 4 combinations, I can have, let's say 2 combinations. So ultimately, my selection time procedure will be reduced by half. So how it is going to happen is that we are taking different parameters which is specific to the beam, like its azimuth angle, angle of elevation, power, receive power, RSRP. These all information will be there in the individual DU. It will learn out of it and send the trained model to a rig where it will taking the information from different DUs. So that's a more of a learning paradigm of an ORAN architecture. And as I mentioned that there are challenges in the centralized learning. Similarly, there are challenges in the federated learning as well. So nothing comes free. We are learning from different entities. There should be some downside of it. So I want to highlight few things. As I mentioned that in federated learning, each entity is learning its own. But let's say that this algorithm is learning on different entities. Each will be having a different capability in terms of processing capabilities, in terms of power, in terms of GPU load, everything. So the learning will not be uniform. So some devices will be taking a decision in a very efficient manner. Some device doesn't have the capability. So it is a challenge to take the input from all the nodes which are having a different capability. Similarly, the data set. So for example, in this example where the beam selection is happening, some DU will have more information about specific beams, while other DU don't have information at all. So how we can combine the information when the data is not distributed? Generally, machine learning assumes that the data is identically distributed. But if non-identical distribution is there, as in this example, it will be adding another problem. The last problem is the malicious user. So if some user generates its own data and try to train the model based on the malicious data. So what will going to happen is that it will impact the global averaging. So the information or the data which is introduced, wrong data or the wrong model introduced by individual identity will be going to impact the global model itself. So one person can harm the whole ecosystem. So there are different research areas which are going on in these specific problems to handle with. But in totality, if we want to really deploy a model on a real environment, definitely federated learning is one of the key learning methodology which can answer many problems which will be there in the coming future. That's all from my side.
All our panelists here, we tried to download the largest possible information in the smallest possible time. So I think they did a pretty good job at it. I think due to the paucity of time, we might not be having a formal questions and answers session, but you can still catch hold of us on the sidelines of the event as you enjoy your lunch. So thank you very much for joining.
Thank you very much indeed, sir. And ladies and gentlemen, please put your hands together for the wonderful presentations we had in this session. As I request our session chair to do the honors on behalf of the organizers to present a token of gratitude and appreciation to all our eminent speakers. We begin by presenting to Mr. Michael Thedault, who is the Chief Technologist. To Mr. Charles Santosam. To Mr. Gil Helliman. To Mr. Gil Helliman. To Mr. Arif Khan. and to Mr. Chitwan Arora. And I would now invite Mr. Shashidharan, MD, Bharat Exhibitions, to present a token of gratitude to our session chair, Mr. Aish Patnagar. And ladies and gentlemen, with that we close the proceedings of technical session 2 and we now break for lunch. The lunch break is of 30 minutes. I would request you all to kindly be back and be seated before